Now, dear students, let us see from using the concept of symmetric and antisymmetric wave function, how a wave function automatically leads to antisymmetry, and antisymmetry is a consequence of Pauli's exclusion principle, and symmetry. Now, I would like to start with a complete wave function. Suppose I have a wave function psi, and it is a representative of the particles to n of a system, and the particles in this wave function, and the particles that we have, these are non-interacting particles. They don't interact at all. So there is no interaction, there is no electrostatic interaction between these particles. And this is what the assumption goes. And, and in that case, these particles can be expressed as the product of the wave functions of their respective numbers in this case. So what can I say is that the wave function of and non-interacting particles can be written as psi of 1, psi of 2, and psi of 3, and so on and so forth to psi of n. Now, let us see that what kind of wave function that can be used to describe this kind of situation that we have here. And let us assume that we have a system of two particles. We have a system of two particles, and these particles are identical. And let us suppose that one of the particles is in quantum state, say alpha, and the other particle is in the quantum state beta. So this alpha is a quantum state for one particle, and this beta is the quantum state for another particle. Now, since the particles are identical, it should make no difference in the probability density of the system, because they are the identical particles. And if we talk about them in terms of probability density, which is given as the square of the magnitude of wave function, there should be no impact on this probability density if the particles are exchanged. And with one of the states being alpha, and replacing the state alpha by state beta, there should be no state of change in the probability density, because we are talking about the same particles here. So how can I go with this is I can write down, I can seek the square of wave function for the particle 1 and 2 is equal to the square of wave function for the particle 2 and 1. And now, if I have to exchange the particle, and something happens to the wave function, let us say if I have a situation like psi of 2, 1 equal to psi of 1, 2. Now, this is the case of symmetric function. This is the case of symmetric. And if we have psi 2, 1 equal to minus psi 1, 2, then certainly this is the case of antisymmetry. Now the question arises here that the function here, the wave function of the system is not itself a measurable physical quantity. We understand that. And so it can be altered in signs by the exchange of particles, because we understand what has this wave function has no, it's not a measurable quantity at all. So if we exchange the particles, that exchange should lead to the change in sign, or it should lead to no change in the sign at the same time. Now, the wave functions that are unaffected, the case of symmetric that we have here, by the exchange of the particles, we call them as symmetric. And the wave functions that of whose sign changes, of whose sign reverses, by the exchange of the particles, we call such wave functions as antisymmetric wave functions. Now, if we have a particle 1, suppose we have this particle 1 in the state alpha, and the particle 2 in the state beta. Now, the wave function of this of this combination, in accordance with this equation, can be written as, suppose that wave function is psi 1, that can be written as psi of alpha 1 and psi of beta 2. That should be the case. And now, if the particle 2 is in state alpha and the particle 1 is in state beta, now this is beta, the wave function is going to be, say, psi second. That will be psi alpha will be for 2 and psi beta will be for 1. That should be the case. Now, because these particles, these two particles are indistinguishable, we cannot distinguish them, we have no way to know any moment whether the psi first or psi second describes the system. And if psi 1 is correct at any instant of at any instant of moment, then at the same moment it's equally possible that psi second is correct. So finally, I can say that the system depends half. The system, the overall system, it stays for half the time in the configuration of whose wave function is psi 1, and the other half in the configuration of whose wave function is psi second. And then I can say that the linear combination of wave functions psi 1 and psi second is giving me a proper description of the system. And two such combinations are possible for these two wave functions. One is symmetric combination, the other one is anti-symmetric configuration. And if I have to write down for psi s as symmetric configuration, for this I will have 1 by under root 2 of psi alpha 1 psi beta 2 plus psi alpha 2 psi beta 1. And this will be for the symmetric wave function. And for anti-symmetric wave function, suppose that is psi a, that will be 1 by under root 2 of psi of alpha for particle 1, psi of beta for particle 2, minus psi of alpha for particle 2 and psi of beta for particle 1. Now, this factor that we have, this is needed to normalize the wave function. So that's how this 1 by root 2 comes in action. And the exchange of particles 1 and 2, if it leaves the wave function unaffected, that will give us the symmetric wave function. And if there is a possibility of if there is a possibility of reversing the sign, then that is going to be the state of antisymmetric wave function. Now, there are a range of important distinctions between the behavior of particles in systems whose wave functions are symmetric, and that of the particles in systems in whose wave functions are antisymmetric. And the most important thing is that in symmetric case, both particles, particle 1 and particle 2, they can simultaneously exist in the same state with alpha equal to beta. And in case of antisymmetric, in the antisymmetric case, what we have is, if we have alpha equal to beta in case of antisymmetric situation, in that case, this psi A that we have will immediately be equal to 0. Hence, what can we say here is that the two particles cannot be in the same quantum state. And this is what led Wolfgang, looks like a gangster, oh no, he's a great man, Wolfgang Pauli. This is what led Wolfgang Pauli that no two electrons in an atom can have same set of 4 quantum numbers that we have talked about. So what we find from this is that the systems of electrons are described by wave functions that reverse sign on the exchange of the particles. And if they don't reverse, we call the wave function in that case is a symmetric wave function. And this gives birth to the particles that we know as fermions and bosons. Fermions and bosons. And for fermions, what we have antisymmetric wave function. And for bosons, what we have symmetric wave function. So if we talk about the experiments that have been carried out on all the particles, and the particles who have odd half integral spins like 1/2, 3/2, and so on and so forth, they have antisymmetric wave function. They have antisymmetric wave function. And by virtue of the exchange of any of the pair existing in them, such particles we include as protons and neutrons and electrons. And they obey Pauli's exclusion principle. They obey Pauli's exclusion principle. And when they are in the same system. That's why when they move in the common force field, each member of the system must be in a different quantum state. And the particles of odd half integral spins are often referred. These particles are often referred as fermions. Okay, so we are having fermions, and if we go into the domain of statistical distribution of the particles, these fermions, they obey is Fermi-Dirac statistics. I'm writing it badly. So they obey Fermi-Dirac statistics. And they are governed by Pauli's exclusion principle. It's a very fundamental tool for understanding the quantum systems where we are dealing with fermions. Now, the particles whose spins are 0 are an integral multiple of n. They have the functions that are symmetric. So the wave functions they have symmetric wave functions, and they are symmetric to an exchange of any pair of them. And if you exchange any pair of these particles whose spins are 0 or positive integers, They do not obey exclusion principle. They do not obey. The point is, they do not obey Pauli exclusion principle. And the particles that do not obey Pauli's exclusion principle, the examples of these particles are photons. The examples of these particles are alpha particles. So we have photons, we have alpha particles, and we have helium atoms, and so on and so forth. And they do not obey exclusion principle. And we call these particles as bosons. Why we call them bosons? Because they obey the statistical distribution that's governed by Bose-Einstein statistics. Bose-Einstein statistics. So these are the consequences of symmetry and antisymmetry of the particle wave function, besides that expressed in the exclusion principle. It is these consequences that make it useful to classify particles according to their nature of their wave function, rather than merely according to whether they are or they do not obey exclusion principle. So with this, I would like to end this piece of work. Bye.